Hello everyone, Kirwa here. So I've been learning OpenGL for the past few days, and in this video I'm gonna explain whatever I have learned. I learned OpenGL referring to Cherno's playlist. Check that out. So let's start with what is OpenGL. It's a cross-platform API, and it gives a standard way for developers to send a command to the GPU. We also use GLFW along with OpenGL, and GLFW is used to create windows and contexts. So I'm gonna run the output of whatever it is I've coded, and then I'll proceed to explain uh, what I've implemented. As you can see, in this window I have two options: clear window, and in clear color I can just set whatever color I want the entire window to look like. Along with it, I have a texture option where I am rendering two quads, and I can use this UI to be able to change their position. So I am going to start with a vertex buffer. So for that, I am going to refer the texture part. So here you can see float positions. Now I want to show what actually happens. So assuming this black rectangle to be a screen and that we want to render a rectangle onto the screen, which is this red portion here. So I've written some coordinates down. The thing with this is that the screen ranges from -1 to 1 in both x direction and y direction. So to be able to render a rectangle in onto the screen, we need to specify coordinates in that range. That's why I've mentioned here 0.5. This should be 0.5 in the ranges of 0.5. But in the code, I have not mentioned 0.5. There's a reason for that. I am using another library and math in OpenGL to be able to transform this, which I'll explain later down the video. Now, this are the coordinates present on the screen. This is what I've translated the coordinates to, and I'm doing that with reference to the screen size. Where here I'm creating the window of 960 width and height of 540. So as you can see, this will be the four coordinates. Now in the main application code, we are using some GLFW functions. We have GLFW window hint, and we are setting basically a version of OpenGL we are using, which is gonna be major version is 3 and minor version is 0.3. So this is OpenGL 3.3. Along with that, we are setting the profile of OpenGL. There are two profiles for OpenGL, one being core and the other one being compatibility. The compatibility one, the core one, has does not support previous versions of or deprecated functions, and we are using the core version here. Along with this, when we are rendering a rectangle, like how I mentioned first, as you can see in what I've demonstrated, we are dividing it into two triangles. So to render those two triangles, we are going to use store data as positions in the array being 0.5 comma 0.5. We'll just go clockwise here. Minus 0.5 minus 0.5 and minus 0.5. Then the next coordinate would be next coordinate would be 0.5 comma minus 0.5. The next one would be 0.5 comma 0.5. Last one would be minus 0.5 comma 0.5. So these are the coordinates of the rectangle, but to render it, we need to specify coordinates for each triangle separately. That would be, first we're going to take this triangle, the lower one. So that would be minus 0.5, minus 0.5, 5.0. Yeah. So this will be triangle 1. And then we need to mention coordinates for the second triangle, which will be 0.5. Again, we need to repeat the data which we have entered. 0.5, and then the top one being minus 0.5 minus 0.5 comma minus 0.5. So as you can see, there is redundancy in data for two of the points, which is being this one and the bottom one. To avoid this, we are using index buffer. So I have created an index buffer below the positions. As you can see, indices. So what it's referring to is we are first drawing a triangle of these 3 points, which is minus 50, minus 50, 50, minus 50, and then 50 and positive 50. Again, we are drawing the second triangle being from index 2, which is 50, minus 50, 50, and 50, and finally we're using the first point again. We are using index buffer to reduce redundancies, else we have to repeat these 2 points again into the vertex buffer. Speaking of which, we also need to learn what is a vertex. Vertex is, like I mentioned in the image, it does not only contain coordinates, it can also contain other values like the color of the vertex. So here we can see we have vertex 1, 2, and 3, and then we have a stride. A stride is basically the length of the entire vertex. And here we are using the size of the data type, each size being 4 bytes. So the entire stride of vertex 1 would be 24. And then we have two values which are stored, which is going to be vertex position. So we are storing position in the image shown and the color. So in color, as you can see, we also have offset 0 for position because it starts at the start of the vertex. Whereas for color, it's offset 12 because it starts at the second position in the vertex. The location is 2, but then there's an offset of 12 bytes before it. So this will be a vertex, and in my demonstration I am passing positions as well as I am passing these coordinates. These are texture coordinates, which I'll explain when I come to textures. Let us just check the classes for vertex buffer, vertex array, and index buffer. So I'm gonna check vertex array first. Okay. Then we also have something called vertex array. So for vertex array, here vertex buffer only stores the data which has to be sent to GPU, but it does not specify what the data contains. In this case, we need a vertex array. The vertex array, as you can see here, will have functions called enable attribute mentioned here, and we have an attribute pointer. So I am gonna first use a website called docs.gl. Here we are gonna search for enable vertex attribute array gl. Now I'm gonna explain this. Okay, it's not enable, it is gl vertex attribute pointer. Okay, so in this we have index, size, type, normalized, stride, and pointer. So I'm gonna mention each of these. So let's start with index. So see, in this we have two values present within the vertex, being position and color. Let us assign indices position to be 0 and then color to be 1. So at index at location 0 we have data for position, and at location 1 we have data for color. That is what index is. Size refers to the number of values you're sending in. So in this case, it would be 3 because it's X, Y, and Z. We are sending in 3 values. And then we have type. Here we are just mentioning the type of data. It would be like a byte or a short, an int, and so on. And then we have normalized. What normalized is it will take the values and it will spread it between the range of -1 to 1, which we can set it as true or false. Now we have stride. As I mentioned before, stride is the size of the entire vertex. Here stride is 24. And then we have pointer or offset. Here pointer refers to offset. In this case, for position, offset would be 0. So pointer would be 0. And then for color, it would be 12. So this is what a vertex is. Now to show all of these things are present using a vertex array. In the start, I mentioned we use core profile. In compatibility profile, a vertex array is automatically created without the person, like the developer, having to create an object of vertex array. But in core profile, you need to create a vertex array. Since I'm using core profile, I'm creating a vertex array object here. I created a vertex buffer layout. This is basically to add data into the vertex, and then we also find out what else is present in the data, like the stride. And this happens whenever I push data. So as I was showing the image there, so I am gonna push, say, position first, then I update the layout to have only position. When I push the color, I'm gonna push the values of color, and then here it will automatically calculate the new stride, the offset for the particular value which has been pushed, and so on. So now that we are done with index buffers and vertex arrays, I think now I'll explain a bit about the pipeline. So this is an OpenGL pipeline. So vertex specification is basically the values of the vertex which we send. Then we have vertex shader. This is tessellation and geometry shader. Keep in mind tessellation and geometry shader are optional steps. Then we have vertex post processing, and then we have primitive assembly rasterization, and then we have fragment shader and per sample operations. So in this, vertex shader, geometry shader, fragment shader are all programmable, and we can send the code to program how it behaves. This I have done in basic shader class. As you can see, I have a fragment shader here and a vertex shader here. As I was mentioning, a vertex shader runs for each vertex. So assuming we create a triangle, it runs 3 times for each vertex of the triangle. We are not going to talk about tessellation and geometry shader because it's optional, but it is usually used for creating more complex geometry within the existing geometry. Then we have vertex post processing. Vertex post processing is used for clipping. It's a step where we calculate clipping and so on. Now, as I mentioned, if this is the screen, the black one, if we have, say, an object to the end of the screen, it is gonna clip out all the points which are not to be rendered onto the screen. I can show you an example of this in the code that we have written. So here we have, say, I move one of this to the extreme end. As you can see, half of the image is clipped out of the screen. This is calculated in Vertex post processing. And then the next part of the pipeline is primitive assembly. Primitive assembly, it is used, it what it does is it connects all the vertices and it's used to find out the shape that has to be rendered. It could be a line or a single point or a triangle. Then we have rasterization. Rasterization is present to calculate all the fragments that are to be rendered. So, and also the pixels within the shape, which all pixels will be included. Next, the fragment shader. This is used for, say, coloring all the pixels. That is one of the most common uses. It runs for every pixel which is present within the triangle. And finally, we have per sample operations. Per sample operations are used for things like depth test and so on. Now that we are done with the pipeline, I want to look at the shader code which you've written. First, we look in Vertex shader. I'm not gonna focus much on text coordinates because it is for texture, which I'll explain later on. And MVP. MVP is it's a matrix which we are using for transformation, and this is the place where the position, like the vertex values which we were sending in the first place, which was -50 and so on, will get converted and normalized via this MVP. So GL position is the place where we specify the position of the vertex. And here, as you can see, we have location 0. Location 0, as I mentioned before in vertex attrib pointer, the vertex attributes, when if it is 0, so in this case, let me just open up this thing. You can see this will be, so if we give location 0, it will check the vertex, and here in 0 we have the position. So it will load the values of position as vec4, and then we are placing it in GL position. At location 1 in the sample image, it's color, but what we are using is texture coordinates. So there it will be, so we are passing through texture coordinates, which I'll explain later. So this is our vertex shader, this entire thing. And the lower part is gonna be our fragment shader. The next thing I want to tell about is in. In refers to input. So we are getting input for position and for text coordinate. And out refers for output. We are going to pass the output values from the function. So here we are outputting texture coordinates. And then in shader fragment, we are outputting color. Now, this I'm gonna uniforms are another thing which I'll explain after the shader code. So this is for texture, which again I'll explain when I'm doing textures. Here I'm gonna change it to uniform color. Yeah, then I'll save it. Okay, so now I've removed texture and use colors. Those rectangles will now be in the color that is specified. This value of color is being passed in the here. Okay, here it is. So what we are doing is, oh, and also I do have to show the code for how I'm handling a shader. Here is the shader class. So this basic dot shader is not like any dot shader is not like any file type. It's what we named the file. So what we are doing is we are loading basic dot shader and we are reading from the file, and then we are gonna iterate through every line until we encounter this hash shader, and we store the code as two different things. So if you can see shader class and shader edge, we have this vertex source and fragment source. So the vertex source which we are gonna use is gonna store these lines, and when it encounters shader fragment, it is gonna start storing these lines in an array, and then we use these functions called, we're first gonna create the shader of a particular type. Here it's gonna be vertex shader or fragment shader, and then we are gonna create, we're gonna take it as a string, the source, and then we are gonna send it to GL shader source. After that, we are going to compile the shader, which we're going to do for both. We're going to compile both vertex shader and fragment shader. After doing both, we're going to attach it to a program, and then we are going to create a program. After the program is created, you can delete the shaders. So here we are deleting the shaders. We are going to first attach the program. First, we're going to attach the shader. Your VS is vertex shader and FS is fragment shader. So we're going to attach both the shaders to the program. And then we are going to attach the program. We're going to validate the program, and then we are going to delete those shaders because now it is not important. After doing this, we can then send uniforms. So here we are sending uniforms. So what uniforms are? It's a way to send data from the from the CPU side to the GPU side. And it here you can see we've put value u color. In our shader source code, we are gonna have a uniform called u color which is present in fragment shader. So this, if we look into the shader CPP, we have set uniform. Now we need to actually find out the location of the uniform, and the location of the uniform is done with this function, get uniform location. Keep in mind, we need the ID and the name of the uniform. So here, that will return us an position of the uniform, which will be an integer. So here we are actually not passing just the name, we are passing the integer value, and then we are passing other values here. I'm going to pass the data for, this is for uniform matrix. Here we are going to pass the uniform location and the value. Now, after uniform, that's how this code runs. So that's how I'm able to render a color. To be able to change the color, I can just change the value of the uniform. Here, set this. So let us say I want to put black. Keep in mind this is also normalized form, so it is not a standard RGBA value. I'm gonna put this. Let's do this. Whatever. Save this, and then we render. I'm gonna see blue color. I can see. This is where we are passing in the color. Now let us talk about textures. So in textures, for textures, I am using a library called SBTI image, an open source library. You just download the header file, create a CPP, and you compile, and that's how we're using SBTI image to fetch data from our directory, and we are fetching data of the file logo. So this we are fetching using SBTI image. I also forgot to mention another thing, which is being another library which we're using called Glue. OpenGL, there's like two different distinctions, being modern OpenGL and legacy OpenGL. By default, you can only use OpenGL 1.1, which is like the first one, and we're using Glue to be able to use modern OpenGL. So most of the other things, say Vertex Array Buffer, to create all of those, you do need to use Glue. And let's get back to textures. So this is my texture class. We're using SBTI image to fetch the texture. And as I was mentioning, we are using texture coordinates also. Here, we are passing in even the coordinates for texture. So this starts from 0 to 1. So the maximum value will be for x and y coordinates is 0 to 1. And then this is being sent to the shader. If you can look at it, we are sending the texture coordinates, and then we are again passing it to the fragment shader. The fragment shader, we are also passing in the data for the texture which we get from texture class. So here another thing to keep in mind is you actually bind a texture to a particular slot, as you can see there. When you bind a texture to a slot, you can access that texture in that particular slot. You can bind it at say 0, 1, and so on. Apparently there are 16 or maybe 32. Depends on the architecture. In this, we are just binding it to 0 because I have only one texture. So here, after creating texture, we are binding that data at uniform at 0, and then we are passing that data using a uniform. If you if I look in texture 2D, here I am passing the texture. So here I'm creating a texture, I'm binding the texture, and then I am sending it via uniform. And when we look at the basic shader, we're gonna take the value of that, and then it'll also take the value of texture coordinates to return the color from the particular texture. Now I'm gonna set the value of texture color to the fragment shader, and then when I run, it should basically show the texture of that. So this is texture. Finally, let's just talk about math. Let's just talk about two other things, because math, I'm gonna use library called GLM. It is a math library specific for OpenGL, which is also open source. I might provide links for all these libraries. Anyway, so we are using GLM, which I do have it in vendors GLM, and we are also using another library called IMGUI. I'm using it to be able to render the UI. So this clear color, texture, these are all not from OpenGL side. This is from IMGUI side. So for this MVP matrix, for this we need to understand transformations. And for me, it was easy to understand transformation when I referred to a YouTube playlist on math. I'm gonna link that. Check that out. It is really good. It actually helped me a lot with how matrices are related to graphics. We are going to use that to be able to basically, we're just multiplying a matrix with the values which we provide, which was like 50 and so on. And then it will, after multiplying, we are going to get coordinates from -1 to 1 on basically the screen coordinates. Now, to use it, first we're going to see. I'm also going to mention about what is, yeah, what is orthographic projection and perspective projections, because they are important. We are going to be using orthographic projection in this case. As you can see in this image, in orthographic projection, all three cubes are of same size, whereas perspective, the size of the cube is reducing. You can think of orthographic to be accurate. There is no diminishing size the further you are, whereas projection, perspective is has diminishing size. It's like when you travel from afar, you see mountains which are like very tiny, but in reality they're like very huge. So that is orthographic and perspective projections. Now here, as I mentioned, I am using orthographic projections, and I'm using it, I think, around here. Oh, not in this. This class. Okay, as you can see, I'm using projection to be orthographic. Now, why we're calling it MVP is because we are going to divide it into three parts. We have MVP stands for model, view, and projection. And the way we multiply depends on whether we are using column order or row order. So since we're using GLM and OpenGL, we just need to directly multiply it as model into view into projections, because GLM is a library meant for OpenGL, and OpenGL uses column order. So you multiply it as PVM. Anyway, what we are doing is, what this stands for is model refers to the coordinates of the object that is being rendered. So in this case, this will be the model values, the 50, minus 50, and so on. This is respect to the world. The view would basically be the camera which we are looking in onto the world. Now the value for the view, it is a bit tricky. So let us say we want to move the camera towards the right. What we are doing actually is moving the entire world towards the left. So that's how view works. And projection is how it is rendered onto the screen. Could be orthographic or it could be perspective. Here we are using orthographic. Now, MVP is just a multiplication of all of these three. We are passing in MVP. Yeah, we're passing it as uniforms. As you can see, we have the model value, which is going to be translation. Here we are setting the values of the respective positions. If I run the program, you can see the values being set here: 200, 200, 200 for this. For object A, for B, it will be 400, 200. These are the model values. And then we are setting view, which is basically one. We are not changing anything in view. And then final is projection. Projection would be our orthographic transformation. This will be projection. We are passing these are all matrices, and then we are passing that to the texture, which is gonna multiply our. So this model value is the position in the real world. So yeah, like I was telling, it is gonna multiply the MVP matrix onto the positions, and then we are gonna get final positions over here. This is what I have learned in the OpenGL course. There are still other topics like lighting and so on, and I will be creating another video on lighting, on frame buffer, and other topics when I complete those. The links for the code will be mentioned. Please do check it out. Thank you.